So let me then move on and introduce our today's speaker, Ilija Zeljkovic. So for those of you who are not familiar with him, he got his PhD from Harvard 2013, working on STM, so visualizing the interplay of structural and electronic disorders in high-temperature superconductors in the group of Jenny Hoffman. And by the way, as a curious twist of fate, Jenny Hoffman is our next colloquium speaker, but this, of course, these talks no longer have anything to do with each other, but it's a funny coincidence. In any case, Ilija then moved on to a postdoc at Boston College, group of Vidya Madhavan. And since 2015, he's a professor at the physics department there at Boston College. He's well known in the community and STM and quantum materials communities, and his group's main interests include atomic scale design of interacting quantum materials, such as topological and correlated electron systems, using molecular beam epitaxy and characterization of the emergent phenomena using molecular beam epitaxy for the growth, and then characterizing the emergent phenomena using low temperature STM. So spectroscopic imaging and also spin polarized, depending on what is needed. And there's been some very recent, very nice work on Kagome metals and superconductors, and that's also the topic of today's talk. And the title is Nanoscale Imaging of Symmetry-Broken Electronic Phases in Kagome Metals, AV3, antimony 5. And with that, Ilija, the floor is yours, and we very much look forward to your talk.
Thank you, Peter. Thank you for a very nice introduction. So yeah, thank you for the invitation. This is great, and thank you all for being here today. So in my talk, as Peter already mentioned, I will tell you about some of our recent work on using scanning tunneling microscopy to investigate a new family of Kagome superconductors, vanadium-based Kagome superconductors, ABS, as I will refer to these particular systems. So I'll show you how we use STM to visualize different symmetry-broken electronic states in these systems. So here's a brief outline of today's talk. I will tell you a little more about Kagome metals in general and expand on what is interesting about this family of Kagome superconductors. I will only very briefly, given the audience, talk about the STM, and then I will mainly focus on two different experiments that we have performed. The first one involves different temperature scales of symmetry-breaking states in cesium-based ABS compound, or CVS, as I will refer to it. And then the second shorter part of the talk, I will focus on this 2x2 charge density wave state in the potassium doped compound, and I will tell you how it reacts or does not react to the application of a magnetic field. Okay, so before I jump into the Kagome systems, I want to very briefly tell you about the lab that we set up at BC. So we do both MB growth and STM characterization. So MB part of this is not necessarily relevant for today's talk, but I still wanted to mention several MBs that we set up for the growth of different quantum materials. So we have a home-built MB system that is primarily used for the growth of tellurium-based topological materials. And then we have two other MB systems that are connected together for the growth of oxides, and then for the growth of selenium-based compounds such as iron selenide superconductors, more recently some of the Kagome magnets and so on. So we interface these with several characterization tools, but our main characterization tool is low temperature STM. So right now we have two low temperature STMs down to millikelvin temperatures with high magnetic field. Soon we'll be able to apply in-plane, out-of-plane magnetic field as well with installation of the vector magnet on our second STM and so on. So one of the nice features about this facility is that we are able to connect all these pieces of UHV equipment that are actually in separate rooms using vacuum suitcases. So we have two vacuum suitcases now that we're able to connect to any of these. Typically, we connect them to the MB, reach out to get the film that we've grown and transfer it to the other MB or the STM and so on. So that way, whatever film or the header structure that we created, we don't expose to air. There's no need for capping and so on before we insert it into the STM. So here's some of the materials that we've imaged over the past 5 years. So in yellow, these are homegrown MB fields that we grow and then characterize using STM. And then in white are cleaved single crystals that we get from our collaborators from around the world, cleave in vacuum and then insert into the STM. So in terms of growth, we focused on topological insulators, Kagome magnets, RN10, 3211, iron-based superconductors, and so on. And then, fairly similar class of quantum materials in terms of the cleaved single crystals. So we've studied correlated oxides, charge density wave systems, high temperature superconductors, and so on. So today I will focus on these two. So our talk is gonna explain what we found in these vanadium-based Kagome superconductors. Okay, so why are Kagome materials interesting? So this was also fairly new to me when we started this less than 2 years ago, when we delved into Kagome systems, and I started learning more about what is so interesting about them in more detail. So the original interest actually stemmed from these systems being spin liquid candidates. So if you look at the lattice here on the right, so you have these corner sharing triangles that are geometrically frustrated, and that can lead to interesting predictions of spin liquid phases. This is probably the most prominent candidate in that category. But this is not the focus of my talk today. Over time, there's been other interesting electronic properties that were also predicted to exist if you have a material with this kind of two-dimensional Kagome lattice. So I'm going to just highlight some of these predictions here. One of the beautiful kind of derivations of a single Kagome plane is the derivation of its band structure. So if you look at an isolated Kagome plane and see what is going to be its electronic band structure, you can see that you will have these Dirac crossings at the corners of the brilliant zone. And then there's going to be a Van Hove singularity above and below that, as well as a flat band that can emerge simply based on geometry of the lattice. Okay, so there's been a lot of interest in generative flat bands, because if you tune the chemical potential exactly right, you can get a lot of interesting phenomena if the chemical potential is tuned right. So there's been a lot of interest realizing this in real materials. Another theoretical prediction that was particularly nice is what happens if you tune the filling to the Van Hove singularity. So Van Hove singularity, kind of like the flat band, also has a lot of localized states. So you can, depending on the interaction and the repulsion kind of strength, you can actually get different phases. So not just magnetism, which is these two below, but you can also get different charge density waves, bond ordering, interesting superconductivity states, and so on. So in the past 5 or so years, magnetic Kagome metals were really at the forefront of this field. So systems like iron tin, cobalt tin sulfur, yttrium manganese tin, and so on. So what unifies these is really the fact they're all magnetic in some form. So either antiferromagnetic or ferromagnetic, and so on. And many of these interesting theoretical predictions were already discovered there. So for example, Dirac dispersions, even wild points, it is cobalt tin sulfur, flat band magnetism. So flat bands were imaged, and interestingly, they generated this orbital magnetism that you can also kind of visualize using STM, and so on. So there's been a lot of work there, but again, it's all involved Kagome magnets. So the natural question that many of us or has been asked is what really happens in these systems if you don't have magnetic ordering anymore. So if magnetic ordering is absent, if you go back to this phase diagram from a few slides ago, you will see that, magnetism is just a very small portion of this kind of two-dimensional space. So can we actually create materials that can create and explore some of these other properties as well? So this is where AVS comes in. So it was discovered in Stephen Wilson's group about 2 years ago. And these are non-magnetic Kagome systems that kind of look like this. So they're nicely two-dimensional, where you have vanadium antimony sheets, which is this gray-red kind of slab, stacked between alkali spacer layers. So the alkali layer can be potassium, cesium, or rubidium. And in my talk today, I mainly focused on potassium and cesium compounds. And then the vanadium is the red spheres that if you look from kind of the top view, they form this Kagome net. So the Kagome net comes from vanadium atoms themselves. So if you look at what was first or soon after the discovery of these systems, what was uncovered, well, it was first demonstrated there's no substantial magnetic moment. So these materials are indeed non-magnetic, very different than iron tin, cobalt tin, sulfur, and so on. They exhibit this unconventional anomalous Hall effect, which was very kind of peculiar at the time, but also this interesting phase transition at about 90 or so Kelvin. So this was later shown to be involved or entail a charge density wave. So a rare occurrence of a charge density wave in a Kagome system that potentially have this chiral character. And theory further predicted topological surface states. So this would make, all these correlated phenomena that I talked about even, or I guess at least this charge density wave state a little more interesting. And finally, what really kind of gathered the interest of the community was the discovery of superconductivity. So in cesium-based vanadium antimony, it was at about 2.5 to 3 Kelvin was the TC, the superconducting TC. So there's a lot of interesting kind of phenomena that were discovered months after the synthesis of this system. And in our work, we basically wanted to investigate using STM how this system cools into the superconducting state. So we're going to use variable temperature STM to really visualize some of these interesting phenomena and actually find something that was not uncovered using these bulk probes. Okay, so the technique that we use is STM. I'm not going to explain anything here, but basically we're going to use topographies, we're going to use DIDV maps and DID spectra to kind of complementary look at different kind of aspects of this system. Okay, so the first material and the first part of my talk involved this CVS. So it's superconducting. Superconducting transition is at about 2.5 Kelvin. And it has this higher temperature phase transition of about 95 Kelvin, which again was based on XRD even at the time related directly to some kind of probably charge density wave. So we take single crystals from Stephen Wilson's group, we put them in vacuum and then we cleave them to kind of rupture them right here. So the vanadium antimony sheets are actually pretty tightly bound. So what we find is that the crystals typically cleave here. We have to leave them at very low temperature. So the lower, the better. And the way we do it actually is just for these systems, liquid nitrogen cleaving didn't necessarily work as well as we'd like. So we put them directly into STM with the cleave bar on. So they are at about 4 Kelvin. And then we quickly take them out and then cleave off the rod and put them back in within like 20 seconds or something. So this is the detail I usually omit, but given the audience, I thought that you might find it interesting. So it's a regular UHV cleaver with nitrogen, just like gave us slightly worse cleaves. But if we did this, we can estimate the cleaving temperature based on like how hot the STM gets once you put the holder back inside. So it's this was the lowest temperature we can achieve, and it gave us pretty good cleaves, like very large flat areas that we can investigate. If you try to cleave this at room temperature, for instance, it will be completely reconstructed. Okay, which is not unique to this class of materials, but maybe related to the alkali nature of this layer. In any case, so we can either image this alkali metal surface or the antimony surface. And these are indeed the two surfaces we get. And this is kind of the large surface morphology that you can see. If you zoom into smaller areas, you can see the atomic structure. Okay, so here's the triangular structure, maybe imaged here of the cesium layer. Here's the topography, maybe somewhere here. Of the antimony layer as well. So what we found is, again, even with this low temperature cleave, the cesium layer often kind of reconstructs. So there's a lot of missing atoms. You can even see kind of based on the pits here. So we really focused on this clean, complete antimony layer in our studies. The first thing we wanted to check is really using STM, to what extent can we access the real true electronic structure of CVS. So for that, we perform DFT calculations in collaborations with our theory friends. We don't do that in my lab in particular, and then compared to ARPES as well. So DFT calculations actually match the ARPES fairly well. So we just wanted to see, can we, to what extent the STM will be able to match them as well. So we use QPI measurements, or what we generally refer to as QPI measurements. So it's electron scattering and interference as a function of energy. So we see nice little ripples on the surface that change the wave vector as a function of energy. This is one data set. We take a radially averaged line cut. So this is a radial line cut of Fourier transform in STM DIDV maps. So what we'll see is essentially a nice circle that kind of grows as a function of energy. And the complete data set kind of looks like this. So this is very low wave vectors that you see here. And if you compare what can it actually match, so it beautifully matches this gamma pocket here. So this is an antimony pocket that we can see that also matches ARPES fairly well. Okay. So we know that as the kind of like first piece of information, there's a very good agreement between calculations, STM, and ARPES. And this is not something that was necessarily often happening in Kagome magnets. So whenever you had strong magnetism involved, some of these calculations actually break down, and they're difficult to actually get an exact match to experiment. But in this case, we actually got a very nice match between all three different, or two experimental techniques and theory as well. Okay, so then we wanted to see what happens as a function of temperature. So I'm going to start our temperature-dependent STM measurements at 60 Kelvin. So this is as 60 to 70 Kelvin is probably as high as we can reasonably achieve with our STMs. And then what I'll show here is the STM topography. So you can see this vanadium antimony ball model kind of superimposed on top. And then if you Fourier transform this topograph on the left, this is what you get. So it's actually nice periodic lattice. So these are the Bragg peaks associated with the lattice that you see in the topograph. But another feature is this 6 peaks that are half of the wave vector to the atomic Bragg peaks. So this is this 2x2 charge density wave state that was also discovered in XRD. So XRD sees this periodicity as well. And if you want to convince yourself by eye, what does this correspond to in real space? Well, you can see maybe this is darker, brighter, darker, bright. So there's kind of a staggered intensity pattern in the topograph itself. So this is again a 2x2 charge density wave visualization from STM that we can see at 60 Kelvin. So this should persist to about 80 to 90 Kelvin. So in CVS, it's about 94 Kelvin, I think. But the interesting thing that we saw, and it took us a little while to really figure out what's going on, is if you cool down. So if you cool down a little bit and cool down all the way to 4 Kelvin, this topograph is going to turn into this. So you see this kind of stripe modulation on top of this Kagome lattice in the background. And if you do a Fourier transform, well, the Fourier transform will give you the same peaks as before. So the atomic Bragg peaks, the 2x2 charge density wave, but also have this peak that maybe in Fourier transform, it's easy to miss if you don't know what you're looking for, but it's very prominent in real space as well. And if you zoom in, it's very clear wave vector of about 4 knot wavelength. So what we uncovered is a new unidirectional modulation with this 4 knot wavelength in these ABS systems that was not apparent for these bulk probes such as XRD and so on. So we want to investigate it a little more detail. So we focus on a large area to get a nice K-space resolution, right? So the larger the real space area, the better the case or the Q-space resolution is. And then we took line cuts along different atomic Bragg peak directions. So there's 3 different lattice directions and investigated what is the fate of these wave vectors as a function of energy. So that's kind of the first taste of any charge ordering, at least from STM. So what I'm showing here on the right is on the y-axis is energy from 0 to 100 millivolts for the 3 directions. So QA, QB, and QC. So what you will see for each one of them is this non-dispersive 2A0 charge ordering wave vector, which is exactly what we would expect for a charge ordering nature of the state. And then for this one particular direction, we also see a very strong 4A0 peak that also does not disperse with energy. So this lack of dispersion of the 4A0 peak, it necessarily signals the existence of a 4A0 charge ordering of some sort. Given the fact that it exists along one direction, we can call it a unidirectional charge order or charge stripe order, if you will. So given that it exists at low temperature, we wanted to carefully map it and see at what point does it disappear. So that was very important just to confirm that this is not some kind of surface reconstruction. You know, if you can warm it up and cool it back down and you can reproducibly achieve it, that means it's some kind of electronic transition as well. So I'm going to show you this line cut in this topograph as a function of temperature. So we focus on the same area of the sample at different temperatures from 12.5 Kelvin all the way to 60 Kelvin here. And then this last peak at 1 is our atomic Bragg peak. Okay, so this halfway to the atomic Bragg peak is our 2x2 charge density wave state. That again exists at 60 Kelvin. It is still there as you cool down. And then this little peak here is our 4A0 charge ordering peak. And if you kind of look at it, what happens as a function of temperature, so at about 48 Kelvin, it's still there. So at 50-ish Kelvin, it's still there. And then about 60 Kelvin, it disappears. So it is a new modulation or new charge ordering state that emerges below 50 to 60 Kelvin. This was surprising. And given that, theoretical predictions of different charge orderings, the Kagome plane didn't necessarily involve a 4A0 wavelength. Given, my Coupe's background and having studied a 4A0-ish charge ordering in BISCO for many years, this was just maybe a fortuitous accident, but in any case, it just piqued my interest a little bit to see, what is really the reason behind that and what does it mean for the physics of the Kagome planes. But in any case, given this is a superconductor, the natural thing that one might ask is, you've shown us the normal state, from 4 or 5 Kelvin to 60 Kelvin. How about the superconducting state? Do these charge ordering wave vectors still exist? So we, cool down to probably about half a Kelvin of electron temperature, effective electron temperature. So well below the 2.5 Kelvin of the superconducting TC. And, we perform the same measurements. We see this 4A0 order as well. So it seems that, this kind of charge ordering persists below the superconducting transition as well. Okay, so I've shown you a lot of different transitions and a lot of different states. So I just want to summarize what we know so far. So at about 94, 95 Kelvin, this material transitions into a 2x2 charge density wave state that breaks the translation symmetry. Then at about 50 to 60 Kelvin, we get an additional charge order that breaks the rotation symmetry. And then at 2.5 Kelvin, we enter the superconducting state with these two charge ordering states kind of carried over as well. So the natural question that arises is, okay, so, this charge ordering or charge stripe order that exists and the rotation symmetry breaking that's clearly there based on STM, to what extent is it really relevant to the Kagome physics? That's, as we all know, STM is a surface probe. So we, given that we're not imaging directly the Kagome plane is kind of buried below this antimony layer. Are we actually detecting any Kagome bands or are we not? So to answer that question, we performed a high resolution QPI measurements. So initially I've shown you some of the high energy QPI measurements just to map a part of this pocket and generally to show that the electronic band structure is consistent with what we expected. But now I'm showing you this constant energy contour at zero energy. So this is the Fermi surface, a simplified diagram of the Fermi surface. Different colors represent different bands. So this circle at gamma point is the circle that, or the band sorry, that we imaged in our QPR measurements before, but there's a bunch of other bands. So we wanted to see, can you actually see them well? And near Fermi level, because quasi-particle lifetime is naturally larger, this is something that you can maybe be lucky and be able to see other bands as well. So what would one see in STM? Well, we can take this constant energy contour, we can autocorrelate this constant energy contour, and if you autocorrelate this thing on the left, you get this image on the right. So we autocorrelate everything within the first and the second billion zone and just assume scattering between the like colors. So we just use a very simplified model to capture basic features of what one might see. And what's interesting is that you see this kind of triple stripe feature along all three directions that come from scattering, oops, give it away a little bit, from scattering between different parallel sheets here. So if we kind of look at what STM sees, well, you're going to observe some similarities and some differences. So we indeed see this kind of like threefold feature near the center. You're going to see this threefold feature at the corner, but that only exists along one particular direction. Okay, so this feature is like very similar, but the other two lattice directions are simply notably not there. So there is also this kind of C2 symmetric quasi-particle interference fingerprint that, again, we can directly see it comes from these bands highlighted by red. Okay, so if you assume scattering between these, you're going to get the scattering wave vectors that we see in STM. So these are, again, vanadium bands. So based on theoretical calculations, we know these bands are primarily characterized by these Kagome vanadium plane bands. So it just allows us to kind of get a glimpse into this Kagome structure and also see that the band structure is renormalized. So we now have this C2 symmetry of the electronic band structure as well. So given the audience, I want to show a little bit about how these QPR measurements actually evolve as a function of energy. So this is minus 18 millivolts. We focus on, to get this K-space resolution, probably about 100 by 100 nanometer, flat, clean-ish region of the space, and then just change the energy and like take the Fourier transforms of the STM DIDV maps. So this is minus 18, and then I'm going to increase the energy, trying to click this fairly uniformly. So you can see there's a lot of information there, but no matter how you look at this, the first thing that you notice is this kind of like C2 symmetric QPI. These are twofold symmetrized Fourier transforms, but I can assure you that in somewhere in my hidden slides I have non-twofold symmetrized, and they look virtually the same. So there is this kind of like primary axis along which the scattering is enhanced. I want to note it's the same symmetry as the Fourier order. Okay, so it's in the same direction. This reflection plane is, or the reflection line is in the same direction. And based on the theory, we know it's directly related to the Kagome bands. Okay, so a typical artifact that one might think of, given STM measurements, is tip artifacts. So whenever you see something unidirectional, well, is it possible it's related to your tip? So the best kind of way to counter that argument is looking at domain boundaries of this ordering with the same STM tip. So here's one domain boundary of this Fourier charge order. So it's denoted by this dashed line here. And what you're going to see is that, this was scanned left to right. So this is indeed like the same STM tip. The unidirectionality clearly switches from the left side to the right side. So here, these stripes are nearly horizontal. Here, they're nearly vertical. So they rotate by about 60 degrees. And the same with the QPI. So if you look at a QPI, these kind of parallel lines here rotate here as well. Okay. So there's a clear rotation of symmetry axis of both the Fourier ordering, the QPI as well. And this cannot be explained by any sort of tip anisotropy. So what we uncovered here is really a true new charge ordering state that somehow couples to this unidirectional quasi-particle interference signature as well. So it very clearly signals that rotation symmetry at this low temperature in our Kagome superconductor is broken, which is one of the nice signature of unconventional superconductors as well. Okay, so the next thing I want to tell you about is, I guess I see there's a question. Should I maybe stop and answer this? Yeah, so the question is that, okay?
Yeah, sorry, go ahead, or I can read it out for those who can't see the chat. So Thomas is asking that what is the real space periodicity of the unidirectional QPI signal?
Well, there's a lot of different periodicities, I guess. So it's like if you look at, this, for example, here, there is the Fourier-Knot wave vector is about here. Okay, so it depends. If you look at this, what is the wave vector here? So maybe the spacing between them is, but 1/8 of A0, but it's, again, there's a lot of wave vectors. It's not as simple that I can tell you just a single wave vector that exists. So, if you reference this one, for example, from here to here, it's going to be much larger. But again, if you go back to where it comes from essentially the distance, the K-space distance between these guys. I hope that at least partially answers Sumesh's question. Okay, so the next part of my talk, I wanted to, yeah, okay. So sorry, I was just looking at the chat. It's hard to balance everything. Yeah, focused on this 2x2 charge density wave state. So even though the Fourier-Knot charge ordering state was kind of a surprise, the 2x2 charge density wave state is really what we came after with our original studies. So there has been theoretical predictions of 2x2 charge density wave state that can naturally exist in Kagome lattices if you have a Vy'kov singularity near the Fermi level. Okay, so you will have this nice nesting wave vector that will be favorable for a 2x2 CDW formation. And there's been other theoretical predictions of different spatial and time reversal symmetry breaking on a Kagome lattice as well. So our original kind of effort was really to understand the CDW state. To what extent is it conventional or maybe not? So in this effort, we're going to use these different systems. So potassium, vanadium, antimony for one simple reason. It does not host this Fourier-Knot charge order. Okay, so this is the only member of this AVS family that at low temperature, it does not exhibit the low range Fourier-Knot charge order. So this really allows us to study maybe the original theoretical prediction of this 2x2 charge density wave state without the existence of something that's clearly unidirectional anyways. So that's why, in the next part of the talk, I will primarily focus on this antimony surface which is the equivalent surface that we've seen before in CVS, but for KVS as well. So this is the topography. This is on the right, Fourier transform of the topography as well, where you can again see this 2x2 charge density wave state denoted by these three symbols. We drift correct our images that I show here, so that's why they're single pixel, and they're nice. It's just easier to kind of compare the intensities across different data sets and across different, So in any case, I can answer more there, but yeah, that's why they're single pixel here, and they're actually quite sharp. The way that we wanted to investigate, is there any sort of symmetry breaking in this state? We examine the amplitude of these three wave vectors as a functional energy. So here what I'm plotting is data from a single DOS map from plus to minus 20 millivolts, where we look at the intensity of this single pixel along the three directions and then plot it as a function of energy. So the y-axis is simply the amplitude of the CDW wave vector. So what you will see is that for two of these symbols, for the squares and the triangles, this kind of intensity profile is really nearly the same. But for the third one, it's clearly different. It's almost opposite, right? If you have a peak here for QB, it's the trough for the other two and so on. So we're still working to understand what is really the underlying physical mechanism behind these differences in the intensity as a function of energy. But in any case, this is something that clearly demonstrates, again, a preferential direction where one CDW wave vector is different than the other two. So this is, again, consistent with a C2 symmetric state that we had before. Just to convince you a little more and just to show you what this looks like in DIDV maps. So what kind of unidirectionality am I talking about? So if you focus on these few energies here, this is DIDV map at 4 and 2 millivolts. So you can see that, at about 4 millivolts, this is the higher point there. You get this nice kind of like unidirectional lines. So this is exactly as one would expect based on the one wave vector being much stronger than the other two. So again, just to convince you, this is not our tip. We can image a domain boundary. These are not often found for this 2x2 charge density wave state, but we can occasionally find something that looks like this on the left. So the domain boundary at 40 millivolts STM topograph might be harder to see compared to -10, but at -10 you can clearly see something's different here compared to the other side. And then if you do the same analysis as before, so you take a DOS map here, you take a DOS map there, you can plot the intensity profile for these two regions. Well, you're always going to see one direction that's different, but that direction is going to be distinct between the two. So what I mean by that is in domain 1, so in the green region, QC, so the C direction is actually the one that's distinct, while the other two are nearly the same. And in domain 2, you will have QB that's different, and QA and QC are nearly the same. So again, the reflection symmetry, or like the C2 symmetry of this state rotates across the domain boundary. And if you fully filter STM topograph to your liking, you can actually see that by eye as well. So just encompassing, this is a filtered STM topograph encompassing maybe QC peak. This is just QB. So you can see the modulations are stronger here and here. So it's another way to visualize this. So this is not a tip artifact. This is a true C2 symmetric electronic state in this 2x2 charge density wave phase. So the last piece of information we wanted to pursue is, does it exhibit magnetic field dependence? So there's been proposals of different orbital loop currents that can generate its charge density wave state that could potentially couple to the magnetic field. So the way to investigate that, we took basically the same data sets over and over again in different fields. So this is just the topograph at 0 Tesla, 2 Tesla, -2 Tesla. We apply magnetic field perpendicular to the sample surface. So we don't have yet the capability to apply in-plane magnetic field, but this is, plus 2 Tesla is autoplane, parallel to C-axis, -2 Tesla is anti-parallel to C-axis. And you can see by eye, I mean, these look virtually indistinguishable. This is like the same region of the sample. We take DOS maps as well, then plot the CDW amplitude as a function of field. So each panel represents a different CDW direction. So this is QA, this is QB, this is QC. X-axis is energy again, Y-axis is the amplitude. Different colors represent different magnetic fields. So what you're going to see is there's really very little within our resolution, almost no difference between different fields along different directions. So what we can, this was left over from different thing I copied, but what we see is no change with magnetic field when we apply perpendicular to the surface. It is repeatable in all areas and samples that we studied. So we studied 3 different systems across 6 different regions, and the symmetry of this state really seems to be C2 symmetry with this one reflection line. So it's not chiral as it was previously proposed, and this is in contrast to the Hassan group that essentially had studied the same material from the same set of sample growers and found that there is a chirality reversal. So they're finding reports that the CW state is chiral based on the slight difference between different CDW peaks. And then, once you flip the field once, you get, some of these peaks change a little bit. So that's, they looked at, the topograph primarily, and then, this was their finding. So the CDW is chiral with this magnetic field dependence, which is not the case based on our measurement. When we carefully image the same area of the sample with the same STM tip over and over again. And our conclusions were actually now corroborated by at least 2 or 3 other groups that looked at that as well. Yeah, this is another data set. We check to make sure there's no tip changes based on, the IDV spectra look nearly identical at different fields. All these amplitudes are really very close at different fields. So it's, yeah, so we are pretty confident that the majority of the areas of the sample do not exhibit any sort of magnetic field coupling with CDW is concerned. Okay, so this brings me to kind of like summary and outlook of what I told you about today. In this vanadium-based Kagome superconductors, we found this surprising 4-knot charge stripe order that onsets at about 50 to 60 Kelvin. And that's kind of like an intermediate temperature between the origin of this or the onset of this 2x2 bulk charge density wave states at 90 Kelvin, superconductivity at about 2 Kelvin. But since then, there's been really like an avalanche of different works and different kind of temperature scales that were found. So, maybe not something that I focused on too much in this talk, but, this system is supposed to have topological surface states, and some of the ARPA's work was able to uncover maybe hints of these topological surface states near the Fermi level. MuSR was found distinct temperature scales, and depending on what MuSR group you ask, they might be close to the charge density wave transition or somewhere below, possibly consistent with this 4-knot stripe order as well, that could be indicative of time reversal symmetry breaking as well. Resistivity measurements show twofold resistivity against closer to low temperature, but maybe also extending all the way to the CDW transition, zero bias mode in vortices in the superconducting state, an exotic pair density wave also in the superconducting state. Most recently, there's been a report of even a nematic phase. So a purely nematic phase is something that should just break rotation symmetry without any translation symmetry concomitant with that as well. So this was found at about 35 Kelvin or so. So there's been really an amazing kind of series of different experimental tools that are trying to probe these systems, and I think pieces are still, falling in place as we speak. But there's a lot of interesting symmetry breaking phases that we've been able to image with STM, but also to look at using other techniques that it certainly makes these systems very, very interesting. In any case, so I will just, for the end, I want to acknowledge people that have been involved in this work. So all the STM measurements have been done by my former student, Hejao, and my current student, Hong Li. And then we have ongoing theoretical collaboration with Leon Zikang and collaborators. And then, of course, the single crystals, all single crystals that we got are from Stephen Wilson's group that, we wouldn't be able to do any of these measurements without it. So in any case, thank you for your time. And I can take any questions.
Yeah, thanks for the very nice talk. And yeah, indeed, there will be questions. So Freek Massey can go first, so I can read out the. Oh, Freek, you can also talk, but I can read out the question from the chat. Okay, maybe I will just read it. So he's asking, can you say something about the superconducting gap structure from QPI measurements below TC?
Yeah, thanks, Freek. Hi, Freek. We've been trying to get high enough resolution measurements to say anything about that, but from now we can't. We haven't been able to take, there's an obvious way to do this. So, you can take 0 Tesla data and then maybe compare it to some higher field data to see any differences in maybe like the different scattering wave vectors intensities and so on. But I unfortunately don't have anything interesting to say about that yet, about QPI below TC.
All right. Then Fabian has his hand up. Fabian, please go ahead.
Yes, towards the end of our first part, you showed a slide where you had the boundary, the grain boundary, and you showed exactly. Show here you have the two Fourier maps, and one can see that in the one on the left there's some extra spots, and I'm not sure. Maybe it's obvious where around the Bragg peaks there's some extra spots. Maybe it's obvious where they come from, and I just find it hard to think in K-space. But given the DIDV map,
the DID here,
yeah,
like
there's some
here?
Exactly, yeah. Where's this coming from?
So this I just kind of briefly glossed over and said that this is like just a complicated system and there's like a lot of stuff. But this is also a QPI wave vector, so we are actually trying to like figure this out in a little more detail. But what I can say is that wave vector right there also disperses with energy as well, and we think we know where it comes from. So there's different parts of the Fermi surface that are, in different shapes. So there's small pockets that I think this corresponds to that also disperse a little bit, but we haven't published that yet. And my students are still trying to finish the analysis, but you're absolutely right. There's other features there that I didn't talk about at all. That could be very interesting. And one of them, yeah.
But why would those three depend on the domain? Because they're not visible in the other domain.
They are not visible. So you mean here versus there?
Yes.
I think there's
That's what I was wondering about.
Yeah. So I still think if you, let me see if I can kind of notate this. So they might be a little weaker, but it's, there's, I can still say, something like, I think it's still a little bit there. So maybe it's hard to see there.
Okay.
But, that's a, perfectly valid question and very interesting. I hope we're going to have an interesting answer to this. So if something rotates as a, across the domain boundary, it just means, if you think of this QPI wave vector as some kind of signal of the electronic band structure, something be gapped or not gapped. So, it wouldn't be surprising if the whole symmetry of the states changes from this to that direction, that the QPI wave vector is also going to change. To me, at least, it wouldn't be too surprising. But yeah, there's a little bit of change there as well. And at this point, I can't say anything more.
Okay, thanks.
Okay, Abdu.
Okay. Okay, thank you very much for interesting talk. I just have one question. That in the last slide, you have shown some flat bottom for the low-lying states. I was wondering whether this is due to interference with the quasi-particles, or this is in the last slide. Yeah, I think one before that.
Or one before.
Yeah. Just to the right, the upper right on the slide. Just one before this. One more. Yeah, this one.
Okay.
So this is due to superconductivity as well.
So this was also taken at this part was taken at 4.5 Kelvin. So it's above.
Oh, okay, it's above. Okay.
Yeah. So this gap, are you asking about the gap? I guess.
Yes.
So the gap is a CDW gap.
Okay.
Yeah. So it's some kind of combination of the 2x2 charge ordering gap and the 4.5 charge ordering gap.
So the system. Yeah, so the system, you initially have Kagome, and you have some kind of electronic order states, which give ways to superconducting states. Eventually. And so qualitatively, what do you think about the mechanism itself? I mean, I know this is something, the holy grail of superconductivity, but what do you think? I mean, this is kind of excitonic or some kind of electronic superconductivity, or it is, this is just a guess. I mean, is it phononic or how, if it's not magnetic, what is it? Could it be?
I mean, I think the jury is still out, and it really depends who you ask right now. So if you think about the, everything that I talked about, in this talk was, a year ago was like, posted maybe a year and a half is really when like a lot of these works. So over the course of a year and a half, there's plenty of work suggesting that, superconductivity is, unconventional, but also conventional, depending who you ask. So it's to what extent is it, if it's not magnetic, I mean, sure, it could be phononic. It could also be some kind of orbital magnetism. There's a lot of theoretical predictions of, the kind of the importance of orbital magnetism in this system. So can that mediate superconductivity in some way? I don't know. But again, this is kind of the next on our to-do list to look at the superconducting state a little more carefully now that we understand the signal like in the parent state. But in terms of the gap, I just want to mention, so the superconducting gap would be tiny. So it's like, you're talking about plus minus 1 millivolts, right? Given the TC of 2. So it's, and on this scale, it's just going to be washed out.
I noticed that. Yeah.
Does that answer your question?
Yeah. That's all right. But are you going to just sorry for last comment? Are you going to put a magnetic molecule on them and see exactly how it interacts with the superconducting phase?
That would be very interesting. I would have to think about in our setup how we can possibly do that, because once you take out this system in, so we have plenty of ways to like deposit something at like room temperature, right? Or higher temperature. That's how MB works. But at low temperature, like with these Unisoko systems, once we don't have a capability to rotate at low, at low temperature and then evaporate to room temperature, which is like, my old room temperature, like STMs could do it, but not these ones. So it's like, we can try, but I'm just afraid, that the surface would reconstruct by the time you evaporate
Of
something
course,
and bring
of course.
back.
You need low temperature evaporation.
But that would be very
sure.
interesting. Yeah,
Yeah.
absolutely very interesting. Yeah.
Thanks, Ilija.
Yeah, sure.
I had a question. Maybe you can pull out the same slide that Fabian was asking with it. I mean, so one of these
the
QPI.
CDW. Yeah, like here maybe.
Yeah, okay. I mean, you can see it here. You can see it in other slides as well. But so,
Okay,
so that I understand.
Yeah, like this.
Yeah. So that I understand correctly. So you have this charge ordering that breaks this rotational symmetry, and then you get these scattering lines between some bands. But then in some other bands, you still have sort of complete symmetry, like this ring around the gamma points.
That's right.
This is how you're saying it works. Okay.
That's right. That's right. Yeah, that's exactly how we understand this. So why is this ring complete around the gamma point? So what I can say, it's different orbitals composing that band. So it's like this ring is actually completely antimony band. So antimony is, not part of this Kagome, like when you think about this Kagome bands, they could have a Dirac crossing and a Van Hove and like all this interesting stuff. So this is coming from vanadium. So this full circle here is coming from the antimony band. So that one's, it's very weakly, if at all, like reconstructed, but it's really this lower temperature ordering is primarily affecting the vanadium bands. That was one of our conclusions as well. Yeah.
Okay, yeah, thanks. That's precisely what I wanted to know. Okay, Jose, go ahead.
Yeah. Hi, Ilija. Thanks a lot for the wonderful talk. So I wanted to ask you about the domain walls that you imaged with STM. And in particular, have you seen bounded states in this domain wall either at, let's say, 60 Kelvin or 10 Kelvin, meaning above or below the second charge density wave transition?
Unfortunately, no.
All right.
Yeah, I mean, you can think of various theories, as you said, to like see domain walls once you enter CDW state or superconducting state, or, it's maybe some regions there's extra like, density of states, but like it's not as convincing as I would like. So it's, which is why we haven't published anything, but, there's nothing that would be just, like very kind of like smoking gun of these edge states, no.
Yeah, great, wonderful. Thanks a lot.
Fabian?
Yes, I was wondering, could you elaborate a little bit on the mechanism that causes the charge density wave? Is it like a Piles transition or is it something else? I know that for the TMDs, there's quite some discussion if it's really a Piles transition of some family surface nesting or whatever.
Yeah, so it's to what extent like phonons play a role versus some kind of electronic transition. I mean, I think I don't think it's like a conventional like Piles transition by itself. I feel like there's not enough evidence that like the phonons actually play a role in this. But with that being said, yeah, I don't know. I mean, all I'm talking about is a 2x2 charge density wave state. This 4 and out, like it's, again, we're working on like to kind of explain it in a little more detail, but like there's no kind of XRD, but in terms
I meant the 2x2 because 2x2, you immediately think of a Piles transition because it's a classic model system where just half the unit cell, where you double the unit cell. So.
Yeah, but it's the classic CDW transition, like it wouldn't necessarily have this like unidirectionality associated with it. So that can actually be explained by different kind of bond orders in different Kagome planes. So there's work for example Rafael Fernandez, where they were explicitly kind of stacking different bond orders on different Kagome planes, and you can connect these little triangles in different ways that would naturally give you rise to kind of like unidirectionality. So it's I guess what I can say is like, yeah, I don't think phonons play a strong role in this. So it's got to be some kind of electronic mechanism, but I don't know to what extent we can fully explain it just yet.
Okay, thanks.
All right. I think what we could do now is we could stop the official part of the talk, stop the recording, and Ilija, if you have a couple more minutes, then stay around if there's some more questions.
Yeah, sure.
But let's thank Ilija once more. It was a really nice talk. Thanks a lot.
Thank you, guys.